Assalamualaikum everyone. Welcome to today's class. I am Ridwan Mohammed Talukdar. In today's class, we will discuss about noise merging and fan out in digital logic circuit. First of all, we need to know what is noise merging. Noise merging is basically a parameter by which we can get an idea about how the logic gate we use and the logic circuit we use is immune to external noise. So, noise merging is the maximum noise that the logic gates can tolerate without affecting its normal operation. In digital logic circuit, we use different types of gate such as AND gate, OR gate, NOT gate. These are the basic gates that we use in digital logic circuit. And in all these types of gate, we deal with two types of values, same states. There is zero state and one state. One is low state and another is high state. This high state is obtained by giving supply voltage, which is 5 voltage, and this zero state is obtained by giving ground voltage or 0 volt. But practically, for various losses, this type of supply voltage and ground voltage cannot be obtained always. So 5 volt and 0 volt, by these two particular voltage, we cannot define the high state and low state. For this reason, instead of single voltage level, we define the high state and low state by range of voltage. One is high state and another is low state. The high state is supposed, in this example, I define the high state logic in between 3 to 5 volt level, and the low state logic is defined at 0 to 0.8 volt level. And this intermediate region is undefined. So, if our voltage level is less than 3 volt, it will no longer be in the high state, it will no longer be considered as high state logic or the one logic. And if our voltage level is greater than 0.8 volt, and it will no more be considered as zero state logic or low state logic. So, for understanding the noise merging, we need to know some parameters. From input perspectives, there are two parameters. One is VIH and VIL. The VIH is the minimum input voltage for which our given voltage level will be considered as the signal 1, that is high state logic. So here you can see that our high state logic is defined between the ranges 3 to 5 volt. So here the minimum voltage is 3. So here VIH is equal to 3 volt. Similarly, VIL is the maximum input voltage for which our signal will be considered as the zero state logic, that is low state logic. And if our given voltage is greater than this voltage, it will not be considered zero state logic. So here the maximum input voltage for which our signal will be considered 0 is 0.5. So our VIL is 0.5 volt. Again, from our output perspectives, there are also two parameters. One is VOH and VOL. Similarly, the VOH is the minimum output voltage for which our signal will be considered as high state logic, and VOL is the maximum output voltage for which our signal will be considered as low state logic, that is 0. Here, the minimum output voltage for which our signal will be considered as the high state logic is 2 volt. So here our VOH is 2 volt, and the maximum output voltage for which our state will be considered as 0 state, and the low state is 1. So here the VOL is 1 volt. So there are two types of noise merging. One is high state noise merging or high noise merging, and there is low state noise merging or the low noise merging. Suppose here there are two logic gates, and the output of the first logic gate is linked to the input of the next logic gate. And suppose the output of the first logic gate is at high state, and we introduce the noise level here. We put the input of the next logic gate. Since the output of the first logic gate is at high state, so our noise should be such that it gets recognized as the high state in the output of the next logic gate. So our noise must be in the range between these two voltages, which are basically the minimum voltage levels for the output and the input voltage to be recognized as the high state. And if our noise gets out from this range, it will no more be considered as a high state logic. Similarly, if the output of the first logic gate is at low state, and they introduce a noise here before the input of the next logic gate, our noise must be in the range so that it will be considered and recognized as the low state logic or the zero state logic at the input of the next logic gate. So our noise must be in the range between these two voltage levels. So we can define our high state noise margin as the difference of these two levels, that is VOH minus VIH, and our low noise margin can be defined as the difference of these two levels, that is VIL minus VOL. These are the two types of noise margin. Basically, we always prefer a high noise margin, and in that case, our logic gate will be more immune to the external noise. Now, we'll discuss about fan out of digital logic circuit. Suppose here there are two gates, one is OR gate and another is NOT gate. The output of the OR gate is connected to the input of the NOT gate. Let us assume the output of the OR gate is at high state logic. And when the output of a logic gate is at high state logic, it sources current to the next logic gates. Since our output of the logic gate is high state, we define our current as IOH. And the value of this IOH will depend on the number of loads. Number of load means the number of the logic gates connected to the output side of the first logic gate. So when we increase the number of the logic gate, the value of the IOH also increases. Typically, the value of the maximum IOH is defined in the datasheet, and the maximum IOH value is basically the maximum current that can be sourced from the logic gate. Again, if the output of the logic gate is at low state logic, it sinks current from the output logic gates. And here, since our output logic gate, since the output voltage of the logic gate is VOL, so our sink current will be IOL. And as the number of the loads increases, the value of the IOL also increases. And also the maximum IOL value is defined in the datasheet. The IOL maximum value is the maximum amount of current that can be synced from the logic gates. Similarly, from input perspectives, there are also two currents. When the output of our logic gate is at high, it will be so the input of the next logic gate will also be high. In that case, some current go into the logic gates. We define this current as IIH, since these are input high currents. And each of these IIH is resulting from the current from the preceding stage, here from the OR gate, which is IOH. So in this case, our IOH equals to 3 times the value of IIH. Similarly, if the input of the next gate is at low state, our there will be some currents flowing into the logic gates, which we defined as the flowing from the logic gates, defined as the IIL, since these are input currents, and these currents from each of the stages will result into IOL. So here our IOL is equal to 3 times the value of IIL. The value of the both of this IOH and IOL must be in the range of between the range of the maximum IOH and IOL specified in the datasheet. This maximum, so IOH will be less than IOH maximum, and IOL will be less than IOL maximum. And these maximum IOH and IOL values define the number of gates that can be connected at the output of the logic gate, from which we get the definition of fan out. Fan out is basically the number of logic gates that can be connected at the output of logic gate. Depending on the number of state, that is high state or low state, we define two types of fan out. One is high state fan out and that is low state fan out. The high state fan out is defined as IOH maximum by IIH, and low state fan out is defined as IOL maximum and IIL. So basically, high state fan out depends on the maximum sourcing capacity, and low state fan out depends on the maximum sinking capacity. For example, if our IOH value is 1 milliampere and each of these IOH value is 0.1 milliampere, we can connect 10 logic gates at the output of the OR gate. And if our IOL maximum value is defined as 2 milliampere and each of these IOL values is 0.1 milliampere, we get 20. That is, 20 number of gates can be connected at the output of a logic gate. And out of these two values of our fan out values, one which is lower will be taken into account. Thank you. This is our basic introduction of fan out and noise margin. Thank you for listening.